as a point of introduction, I'm a mathematician and statistician by training, now a university assistant professor at the Stats Lab, which is a sub-department in the Department of Pure Mathematics and Mathematical Statistics, and also a fellow and director of studies for Corpus. I'm relevant to this topic because I grew up in Wuhan, so I know the city very well. I'm gonna perhaps give you some, well, hopefully some insights into this epidemic when it first broke out. We'll talk about two things. First, what could we have said about the epidemic outbreak in Wuhan if we go back in time and if we were in January and February 2020? And I also want to talk about why mathematics and statistics are critical to answer this question correctly and to get a good understanding of the epidemic when it was still in a very, very early phase. Some caveats, I'll refer to the disease as COVID-19, as you all know now. But back in that time, in January and February 2020, this is still really, really early in this epidemic. And that name actually hasn't appeared. So it was called the novel coronavirus or 2019 nCoV, which is now just was a temporary name for the novel coronavirus back then. And this tells you that actually, when we are looking at these events that happened 2 years ago, there's potentially a large hindsight bias. So just keep that in mind as you are going through these data and analysis with me. So in the first 20 days in 2020, the most burning question was, can this disease, this novel coronavirus, COVID-19, be transmitted from human to human? And this here, I'm giving you a table of the total number of confirmed cases. So it's the cumulative number of confirmed cases in Wuhan by the date of press release. So starting from December 31st, 2019, which is when this sort of new disease was first officially recognized, then all the way to the end of January 2020. So if you look at the official press releases by this health commission in Wuhan, they were clearly very optimistic during most of this period. So on January 5th, they said there was no clear evidence of human-to-human transmission. January 9th, they said can be prevented and contained, so don't worry about it. This is, I think, January 14th, they said no clear evidence and the risk of sustained transmission is low. But they changed the tone completely. It was a U-turn basically on January 20th, when they said that this novel coronavirus can certainly be transmitted from human to human. So there is a big, sharp change at the end of this period. So what happened? So what happened really, I think at least part of what happened, the reason behind this is that data can lie and data will often lie. So if we look at this table again, maybe I just go back to the previous page. If we go back to this table again, you can see when these conclusions are drawn, and these are indicated by different colors in the table, you can see that at least from just this table, these conclusions are relatively they're quite reasonable, I guess. Nothing seems really been going on until suddenly on this date, the 20th of January, that you see a huge increase in the number of cases. But there are a couple of suspicious observations. First, the number of cases actually dropped on 11th of January. And then there was a long period, almost a week, that this number just stayed flat. So what happened? Well, basically, this is an artifact in the data. The epidemic was fast growing in the city, but it was not captured by the number of confirmed cases. Actually, from like between January 5 and January 11, there was this is the period where this coronavirus was officially recognized. So they use a different diagnostic criterion. So that actually led to a drop in the number of cases. And then for the next week, basically everyone was waiting for the PCR test to be developed and distributed. So having a flat curve doesn't mean this epidemic has stopped. If you look at evidence elsewhere, there's actually some indication that this is perhaps quite a high-risk situation. The pathogen is a coronavirus, is far from the first human coronavirus. So we sort of know that it has the capability of transmitting across humans. And actually in late December 2019, genomic sequencing already identified this is a SARS-like coronavirus, and SARS was a major epidemic in the beginning of this century in China. So just from these evidence, it seems we really need to pay attention to this potential disease outbreak. And there are some other evidence which were mostly found in hindsight that actually in several hospitals in Wuhan, they were already seeing rapidly increasing number of suspected cases during this period. Okay, so moving to the next period, so from about January 20th to the end of February 2020, the next important question is how infectious was COVID-19 in Wuhan? How dangerous this epidemic is to the whole country, or actually to the whole world. So to answer this question, now we really need to bring in some mathematics. So there are two quantities that are most important when we want to answer this question quantitatively. So the first is, not everybody knows this, I guess, this is a basic reproductive number, or R naught. It's roughly interpreted as the average number of infectees per infected person in the beginning of an outbreak. So for SARS, the estimated R naught is 2 to 4. MERS is another human coronavirus, and that's actually has an R naught less than 1, which means that it's unlikely, very unlikely that it will have a large outbreak. And seasonal influenza has an R naught that's believed to be less than 2. So this is quite important in modeling the epidemic outbreak, this number R naught. However, it is very difficult to estimate, and actually to even define it precisely, often that requires a mathematical model. So, it's not a very easy number to obtain, as I'll explain towards the end of the talk. Another quantity that's interesting is the initial doubling time, which is just how fast this epidemic is growing in like a temporary sense. So this is arguably more relevant in early outbreaks because it better captures urgency, and also it's much easier to estimate than R naught. Two initial studies that really sort of shaped our understanding of the COVID-19 pandemic was these two papers, one published in New England Journal of Medicine, the other in Lancet. So these are absolutely the top medical journals. They were published towards the end of January 2020. And both of them found that the initial doubling time, they estimated the initial doubling time to be around 6 to 7 days, or 6 to 8 days. And the R naught was about 2 to 3. Now, in the brackets, I've given you 90%, 95% confidence intervals. Now, that's perhaps a new concept for you. And what we mean by confidence can be made precise using mathematics. It's a bit beyond, I guess, A-level statistics. But basically, you can treat these numbers as some kind of interval estimate of these quantities that we have a large confidence in. So we think most likely, at least these papers think most likely the doubling time and R naught will fall in this region. Okay. I guess one thing I wanted to point out, which will come up later, is that for the second paper, these confidence intervals are actually quite narrow, which is actually a bit surprising for the reasons you will see in a few minutes. So I'm going to present some reanalysis of the same data that these two papers use to give you a flavor of the mathematical tools involved and the computational tools involved in computing these numbers. So this reanalysis is going to be based on this model called the Poisson log linear model. So it's really a very basic model in statistical modeling. And what it basically says is, if I say y sub t is the number of incidences, which could be the number of new cases or the number of people showing symptoms, depending on how you define incidences. So if yt is the incidences in day t, then this model says, first of all, yt is a random number, so it's a random variable. The distribution of the random variable is a Poisson distribution. And the mean of basically the average value of this number is log linear in time. Meaning if I take an exponential on both sides, I can see this expected number of incidences is growing exponentially in time. And this, this exponent r is directly related to the doubling time. So doubling time is just log 2 divided by r, if this r is greater than 0. Okay, so the Poisson log linear model gives us a tool to estimate this coefficient r. Okay, so if you look at the first paper, this is an excerpt from the paper that that describes their statistical analysis. They really did not give much detail besides that they used data with the cases with illness onset between December 10 and January 4th. Then regarding the model or anything about related to the implementation of the model, they don't really say much. Okay, so by just looking at this transmission model formulated with the use of renewal equation, it sounds like they're trying to use some kind of perhaps differential equation models, but they didn't specify the model in the paper. So instead, let's just use this Poisson log linear model to fit the data. So I'm showing you two plots. On the left, this is the number of cases who showed symptoms on each day. And these dashed lines are the period that the authors used to fit the data. Okay, so we could fit this log linear model, which is the red curve here, using the data in this period. And that gives you this sort of exponential growth. And you can look at that in the log scale. So that would become a linear curve. And here, this is showing you the logarithm of the cumulative number of cases over time. So you can see, well, at least in this period, this curve seems to fit the data reasonably well. And the corresponding doubling time for this red curve is 3.7 days. So that's much shorter than the estimated number given by the original paper. So the original paper would correspond to a growth curve like this blue one, which does not seem to fit data at all. Okay, so you may wonder why the number of cases decreased since around January, perhaps January 10th, and that's because most of the people who showed symptoms here, they were not identified when the paper was published. So there was a lot of sample selection bias in the data set. But it seems that for this part, at least it's reasonable to say that perhaps most of the cases were identified. Okay, so if we look at the second paper, it's a bit more advanced, and they told us a bit more about how they arrived at those estimates. So they said they used 78 exported cases from Wuhan to areas outside mainland China. They used this so-called susceptible, exposed, infectious, recovered, or SCIR model. It's basically like a differential equation model that classified people into 4 different classes: the susceptible, the exposed, the infectious, and the recovered. And then they build like differential equations to explain how people move between these classes over time. This is very common in epidemic disease modeling. But this model does not really account for this kind of case exploitation. So for that, these authors use the non-homogeneous Poisson process. Okay, then they said they estimated this R0 using a method called Markov chain Monte Carlo. This is really quite an advanced Bayesian statistics method. And then finally, they described a little bit about their implementation. They said that they used cases with symptom onset between December 25th and January 19th. Something that's not mentioned by the paper is that actually if you use this criterion, you don't get all the 78 cases. Those are the cases mostly who had symptoms after January 19th. So this criterion actually would only leave them with just 17 cases. Okay, so if we fit a Poisson log linear model to data set provided by these authors, you would get a similar point estimate. So here you would get a doubling time of about 5.9 days, and that both this red curve fitted using the data and this blue curve, which corresponds to the doubling time found by the authors, seem to match the data fairly well in this period. Oh, sorry. These are actually this blue curve is not does not correspond to what this red curve doesn't correspond to the author's estimate. So this I'm switching things around. So this blue curve is obtained using data before this date. So I think that's January 29th. Sorry, January 19th. But if you just extend 3 more days, you would get this red curve, and that give you a sharper increase. So that actually would give you a point estimate that's 3.9 days. Okay. the thing I want to point to, I want to point to is the confidence interval, this interval estimate that sort of captures the uncertainty of our estimate. So from this model, the confidence interval for the doubling time would be 3.4 to 15.7. So there's really a big uncertainty about this number. That's totally different from what the authors have said in the original paper. And I think this is much more reasonable because these curves are fitted using just 17 cases. So there's not really much information you have in this data set. Okay, I'm not gonna just quickly talk about some other ways we can think about modeling epidemics. So beyond just sort of trying to get a curve of case number and trying to fit some curve to that, you can also think about each patient with this disease as a point process. Basically, a point process means that several events have happened to that person at different time, and perhaps at some random time. So for each patient, you can characterize them using these things such as when they started to have exposure and when they ended their exposure. So because in these excuse me, in these cases exported from Wuhan, you sort of have a high certainty that they were exposed to the coronavirus when they were in Wuhan, and you know when they traveled, so you have a good idea of when they were exposed to this virus. And then at some point, patients showed symptoms, and maybe they were hospitalized, and finally they were confirmed. And some patients probably the data would tell you when they were discharged from hospital. So basically, each patient corresponds to this point process that records these events and when they happened. So this gives you much more information than just summarizing the number of patients with a symptom onset on each day, right? So this tells you much more about the individual patients. So here's a better statistical model for exported cases that use more information. So if we look at these three key events in the trajectory of one COVID-19 case, beginning of exposure, end of exposure, and onset of symptoms, I'm going to call it B, E, and S. These are very useful because it helps us to infer the unobserved time of infection T, which really is the beginning of every case, right? I mean, I'm a bit sick from some sore throat now, but I started the time when I started to have the symptom. It's not that it's not the most relevant thing in terms of thinking about epidemic. The most important event is when I got infected. So that's the time T that's almost never observed. But we know logically it should be between this exposure period. And furthermore, we know symptom onset S minus this time of infection is the incubation period. Although we don't know the exact incubation period for each person, if we know roughly how the incubation period are distributed over the population, then we can impute this latent time of infection, at least in a stochastic sense. Okay, so if we think about the time of infection for people, for these exported cases, people who were infected in Wuhan and then traveled elsewhere, we can see that this simple exponential growth model actually is not very suitable because of the travel quarantine. So basically, everyone in Wuhan was not allowed to leave the city since 23rd January 2020. So that means that everyone who are already infected by 23rd of January 2020 cannot leave the city and cannot be found as exported case. So that's why instead of assuming the density of the infection time grows exponentially, a better model is to say the density is the exponential growth corresponds to how likely they are infected on each day, but times a linear or a piecewise linear term. That is, as you approach this time of travel quarantine, you are less likely to travel out of Wuhan, and until if you're infected after 23rd of January 2020, then you cannot leave, so you cannot enter this data set. So a much more reasonable model, I think, would add this component to the density function of this infection time. So now if we put these two ideas together, imputing the time of infection and modeling time of infection, we could get a different estimate of the doubling time. So in this figure, I'm showing you, I think, about 50 cases. These are almost all the initial exported cases in Asia, in Hong Kong, Japan, Korea, Macau, Singapore, Taiwan. And each one basically represents a point process for a patient, right? So this, if I zoom in a little bit, so if we look at this last case in Taiwan, this is when they were confirmed. This is when they showed symptoms. This is when they left Wuhan. So basically, by using the incubation period distribution and the constraint that they must have been infected at this time before they leave Wuhan, you can sort of get an imputed distribution. It's like a histogram of when these patients were infected, and you can do this for every patient. Now, if you combine all these little bars and you just aggregate them and average that, that would give you the chance of someone being infected on each day and then leave Wuhan and be identified as exported cases. So move to my next page. Okay, so then we can really use this idea to fit the growth model. So here I'm showing you two fits, one using the logarithm of the infected of the density of the estimated density of the infection time over date, and this is the logarithm of the infection over the days before January 24th. So that would correspond to the improved model that we talked about, and they would give you quite different estimate of this growth coefficient R. So for this panel, it basically assumes an exponential growth for these people. So the logarithm of the infection would be linear in time. But for this right panel, if we make this model that the density is exponential growth times this linear term, then if we take the logarithm of the density divided by L minus T, this linear term, that would be linear in time. So the slope would be the growth coefficient R and this would hold for before the lockdown L. Okay, so they would give you quite different estimate of the slope, and notice that this right panel. So for both cases, these slopes were estimated using the data before January 20th. And you can see that in the right panel, this curve, this line fits the data much better for the next 3 days. Whereas in this left panel, this really falls off and doesn't match this model. Okay. So potentially because of that selection on the data, so because we only use exported cases, you could have a large discrepancy in your estimate. Okay. Go to the next page. Okay, so just a few words about estimating R0. So there are really 2 ways to think about this basic reproductive number. You can think of it as a derived parameter from these compartmental models. So the SCIR model, susceptible, exposed, infectious, and recovered. That differential equation model I talked about is a special kind of this class of compartmental models. So from those models, you can derive this R0 as a function of parameters from that model. Another way to estimate R0 is through this formula. That's R equals to 1 minus M of minus R, where M is the so-called moment generating function of the generation time. So moment generating function is a concept in probability theory. We haven't, of course, we haven't encountered it yet, but it would be part of every probability course in a university. And generation time means that this is the time between 2 consecutive infections. So if I pass this virus to my friend, then the time between my infection and their infection, that's the so-called generation time. And R here, this little r here, is just the growth exponent, which corresponds to the initial doubling time. So the second approach is, I would say, a bit easier, because once we know the growth exponent from the initial doubling time, all we need is the distribution of the generation time, and that can be estimated from some carefully constructed data where you know who infected whom and who and the time they showed symptoms. But both approaches would require estimating some external parameters, things like the distribution of the incubation period or generation time. And surprisingly, I guess this would be surprising, at least to a serious statistician, none of these early COVID-19 studies considered uncertainty in external parameters. And by that, I mean, we're not quite sure how long the incubation period of COVID-19 is. It could be maybe on average 3 days or 5 days or 7 days. We just don't really have a very precise understanding of it. And that uncertainty affects how well we could know this number R0. I'm gonna give you an example. So this is a bit advanced, but basically here I'm showing you 100 possible values of the mean and the standard deviation, which are just quantities characterizing a distribution, right? So for example, this point means that it is estimated that the incubation period has a mean that's about 4.7 days and a standard deviation that is about 1.5 days. So these two quantities are the most basic statistics about a distribution. And using data, we can't really pin down where these numbers are. The best we can say is it's roughly in this region, and here are 100 possible values of these numbers. So if you look at these two numbers, here corresponding to a mean incubation of 4 days, and this is actually the generation time. So mean generation time of 4 days and a standard deviation of 2 days. And another possibility that's the mean is 6 and the standard deviation is 4. Both of them seem likely based on this estimate of the of the generation time. But they would lead to quite different estimate of R naught. So the red curve corresponds to this point, and this shows you different value of R naught when the doubling time is given by these, and the exponent which corresponds to different values of R. So you can see, for example, if I think the doubling time is 2.5 days, then this red estimate of the generation time would say that my R naught is maybe just a little bit over 2.5. But this blue estimate of the generation time distribution would say that the R naught is almost 5. So there's really a large discrepancy. And that's really, I think, fundamental in understanding and interpreting these estimates of R naught. Most of the time in the media, you see some number, some estimated number of R, but rarely they speak about uncertainty. And even if they do, they really account for all levels of uncertainty when they derive those intervals. Okay, so let me wrap up. So what did we talk about? We talked about how data can lie and will often lie. And we talked about how we can tame the data by a good understanding of how they're generated and applying the appropriate mathematical tools. So it's really a cooperation of practical knowledge and mathematical knowledge. There are a few advanced mathematical statistical concepts that I talked about in this talk. And here are some courses in Cambridge that talked about these concepts. Okay, so that's all from my side. So perhaps question time.
So has anyone got any questions then for Dr. Zhao at all? Let me get my questions. To see anyone's thinking. It was so good that you've answered all of their questions in advance. I actually have a question. Oh, so a couple of questions are just.
Okay.
So Hugo wants to say, so on slide 15.
Yeah.
Hugo asked, how were the rings calculated and what do they show? So I assume you're talking about the left-hand panel.
Here. These are, this is related to a concept called the posterior distribution. So basically, we don't know the mean and the standard deviation of the generation time. So we try to estimate it, but we can't estimate it precisely. There's some uncertainty about it. So we really think about the possible values of the mean and the standard deviation of the generation time. So it's a distribution on two variables. So there are different ways to visualize the distribution. I'm giving you two ways. These points are basically random samples from this distribution, which give you some ideas of how likely each that these values would be in this estimate. And these rings, they're basically contours that show you sort of this is the most likely region for the mean and the standard deviation. This is the next most likely region, and the next, and it goes on. So it sort of so it really, this is trying to plot this distribution density, which is a two-dimensional function. So it's like a surface, but instead of visualizing a surface, I'm projecting that surface onto the plane, and this is just giving you the contours. This is like making a map. So this is giving you the if you think about the density function like a mountain, it's giving you the contours of the mountain.
James asks, from the data we now have concerning the infection rates of COVID-19, how does it compare to what was initially estimated?
Okay, so it's difficult to directly compare these estimates for several reasons. So first of all, as you all know, the virus mutates, and now we have a very different variant, and I think it's potentially much more infectious than the original variant. Another reason it's difficult to directly compare is these are in different settings in different cities. So Wuhan is a very populous, densely populated city, which may be very different from Cambridge, for example, which is not rural, but it's a much smaller city, right? So you can imagine the kind of scenarios that these viruses are passed around are quite different in these places. So it's really hard to say, like, given what we now know, can we really say much more than what we much more about the initial epidemic in Wuhan, especially in terms of these epidemiological parameters, and they're just quite in quite different settings. And I'd like to say that that's partly why understanding the initial epidemic is so important, because that's kind of where the baseline is. All the new variants are compared with the previous variant. We say the Delta variant is, I don't know, 50% more infectious than the original variant. That's because of when we look at the evolution process of these different variants, that gives us a sense of the infectiousness of the variant. But if you want to really understand the R0 of the Delta variant, we have to have a good understanding of the R0 of the original variant. And that is really, you can't really get that other than looking at the original data and trying to really get something out of a very, very noisy data set.
Someone asked, I don't have their name, someone asked, how did you get into epidemic modeling?
Because of this connection. I was not I'm a statistician, and I don't know much about epidemic modeling before COVID-19, and so I heard about this looming disease outbreak at the end of 2019, and I sort of saw how it unfolded. I saw a lot of rumors, and then a very close relative of mine got diagnosed with the viral pneumonia, and they could not confirm it was COVID because they don't have enough PCR tests. I remember that's 29th of January 2020. I heard about that from my parents, and I decided, well, I should perhaps use what I know to do something about this. So everything here basically came out of, I mean, these plots came out of some of my work on this topic. It's a bit daunting in the beginning because I don't know much about epidemic modeling, but I quickly realized that even people who are supposedly expert in the area, they actually got a lot of their statistical analysis wrong. Like I gave you some examples published in top medical journals that I think the results like that have results that I can't replicate, and so I think this is sort of related to why mathematics could be really a good undergraduate major than other things. Like even if you want to do like epidemic modeling, it's probably a better major than I don't know, medicine or public health or epidemiology that directly addresses this problem. Because if you do mathematics, you really think from the very basics, and you build up your knowledge and build up the foundations for these more applied problems. And then once you have a solid foundation, you start to realize that these kind of applications related to mathematics and statistics are not too difficult to understand, and often coming from a basic foundational perspective, you can actually bring some new insights into these fields.
Someone asks, at what point can we say that the value calculated for R is accurate? It seems to get more accurate as time goes on, but surely is it always changing?
It's a good question. I mean, in statistics, the uncertainty of your estimate depends critically on the sample size. And that's why with just 17 cases, you really can't quantify these values very well. You can maybe get a very rough estimate, but these kind of confidence intervals are usually very, very wide. Now with more data, I mean, well, unfortunately, that means we have more people suffering from this disease. But from a statistical point of view, you would get more accurate estimates. But as I said, we are dealing with a changing environment. It's really hard to define just one version of R, because really we're just trying to use a number to describe a large number of social settings where this virus could be passed around, right? And you can imagine the R for, I don't know, an indoor environment is quite different from the R in an outdoor environment. So this R is sort of basically a number that summarizes, it gives you some idea of how sort of infectious this virus is at this moment. But really that's a very, very crude statistic. It's if you really break it down to these very detailed scenarios, then the values are different. So you could say that we got a very accurate estimate in the broad setting, but if you really break it down, then you still have a lot of uncertainty.
Nazia asks, how are the confidence integrals calculated for the data produced?
Okay, so for these intervals that I talked about from, so there are many, or I should say there's many different ways to do this. For these intervals, I gave you from the Poisson log linear model. These are quite standard. You would learn it in any sort of, in your sort of second or third statistics course in any university, I think. It would tell you how these intervals are obtained. Another way to do this is to compute this confidence interval. It's actually not called confidence interval, but credible intervals. Is that if you are approaching this problem from a Bayesian perspective, then you would get this kind of posterior distribution, and then you could, in this case, get like a region with 95% of the posterior samples. So in this case, that would roughly correspond to this outer ring. which contains about 95 points out of these 100 points that are generated. So that could be your posterior credible region. So it's no longer a confidence interval now because it's two-dimensional, but that's a region that roughly corresponds to 95% of your estimate.
Great. Have we got time for one more, Dr. Zhao?
Yeah, sure.
Is that okay? So there is a long question, so I'll read it out, so bear with me. I know, how do we agree on fundamentals within statistics? For example, I've seen that two proposed definitions of an outlier are that it is within 2 standard deviations from the mean, or 1.5 IQR above the upper quartile or below the lower quartile. How do we decide that these are reasonable definitions? Why do we use these numbers and these parameters to come up with these definitions? Sorry for the long question, but I did really enjoy the talk.
Yes, that's a really interesting question. I think this is really related to a fundamental difference sorry, between mathematics and statistics. Although they're often taught together, the fundamental difference is that in most part of mathematics, it's about deductions, proving theorems, establishing something rigorously. But in statistics, the main goal is actually to make inference, so to infer conclusions from data. So deduction, so in some sense, it's called the induction. Which means that we're never certain about our conclusions. Our conclusions are based on our experience. So that's how I see why mathematics and statistics are quite different subjects, because they're about different kinds of reasoning. Statistics needs a lot of mathematics because it gives the mathematics gives us principles about statistical inference. What is a good statistical inference? What is a poor statistical inference? But in many ways, there is no absolutely correct or absolutely incorrect statistical inference. It's because of the nature of statistics, it's always inductive. We're never quite certain about the conclusions we make, but we try to attach a level of certainty for our conclusions. So we say we're 95% confident in some mathematical sense about our interval estimate. So that sort of level of confidence is really important in statistics, and how to formulate that rigorously requires a lot of mathematics. Now back to your question. So there are different definitions of outliers, which is totally expected because of what I just said, because it's not an entirely objective definition. There are different ways to think about the same phenomenon in our world. And in some cases, one definition may be more accurate or more reasonable than another, but that's not always true. Now, mathematics will tell us something about when one definition of outlier is perhaps more reasonable or more precise than another in some cases, but it's never like a black or white conclusion. So you could use both definitions of outliers, I would say. And this is related to an area in statistics called robust statistics, which is about come up with conclusions that are robust to deviations from your assumptions. So between the two examples you gave, this definition using the interquantile range would be more robust than a definition using the standard deviation, because the interquantile range is a more robust statistic of a distribution.
Thank you.